Why is everything you see, from stars to smartphones to your own body, made from just a handful of tiny building blocks? Why can some particles pass through your entire body without hitting anything, while others stick to matter like glue? And why does the universe seem to run on rules that are far stranger than anything we experience in daily life? Welcome to particle physics, the study of nature at its smallest scale. Imagine sprinkling sand on a table. No matter how much you crush it, it eventually stops breaking. Particle physics asks, what happens if you keep crushing matter beyond that? How small can you go? If you keep zooming in past cells, past molecules, past atoms, you reach protons, neutrons, and electrons. But even those aren't the true building blocks. Protons and neutrons are made of even smaller particles called quarks, held together by a powerful force. Electrons are not made of anything smaller. They are truly fundamental. So the universe is built from a small cast of characters. Quarks combine to form protons and neutrons. Leptons, like electrons and neutrinos. Bosons, the force carriers that make forces work. This entire collection is organized into a framework called the Standard Model, our best explanation of how particles behave. Now let's go deeper, because this is where things get interesting. Quarks come in 6 flavors: up, down, charm, strange, top, bottom. But the everyday world uses mostly up and down quarks. Every proton you've ever seen has 2 up quarks and 1 down quark. Every neutron has 1 up quark and 2 down quarks. Electrons belong to a different family, the leptons. They orbit atoms and define chemical behavior. Neutrinos are also leptons, but they are so ghost-like they pass through Earth as if it isn't there. Trillions pass through you every second without touching a single atom. Now, forces between particles don't just happen. They're carried by special particles called bosons. Electromagnetism uses the photon. The strong force, holding quarks together, uses gluons. The weak force, responsible for radioactive decay, uses W and Z bosons. And gravity, well, gravity's particle hasn't been found. We call it the hypothetical graviton. Then there's the Higgs boson, discovered in 2012. It's responsible for giving mass to particles. Without it, everything would fly around at the speed of light, unable to form atoms, stars, or life. All of these particles interact in ways predicted beautifully by the Standard Model, a theory so accurate that experiments match its predictions to many decimal places. But here's the twist. The Standard Model, as powerful as it is not the whole story. It cannot explain dark matter, dark energy, or gravity on the quantum scale. It cannot explain why the universe has more matter than antimatter. It cannot explain the exact masses of particles, only that they have mass. This means particle physics is still full of mysteries. What is dark matter made of? Why does the universe exist at all? Are quarks and electrons truly fundamental, or made of something even smaller? Is there a deeper theory waiting beneath the Standard Model? And that curiosity opens the door to the next chapter, the search for new physics beyond what we know today.